All right, so we're gonna do course schedule 2 on LeetCode using Kahn's algorithm. So if you saw my previous video, I did this problem using BFS, but we're gonna use Kahn's algorithm for this one, or this time. So they give us two things. They give us a number of courses and they give us some prereqs. And the thing on the right is the course we have to take in order to take the course on the left. So the thing on the right is the prereq and the thing on the left is the class we take after the prereq. And they just want us to return an ordering of the courses that we have to take to finish all the courses. So the fancy phrase for this is they want us to topologically sort the courses. Okay, so before we get started, let's create an adjacency list because in Kahn's algorithm, it's essentially a breadth first search. So we need an adjacency list to efficiently loop through our neighbors. So let's call this adjacency list equals new hash map. And actually, really quick before I get into the code, let's just go over the two quick steps of what Kahn's algorithm is. So essentially, we just want to process all courses, or you could say all nodes, with no incoming edges. So essentially, if they have no incoming edges, then we can go ahead and add that course to our result. But and then after we do that, we're going to delete those nodes outgoing edges, or we're going to simulate deleting those nodes outgoing edges from the graph. And then we just repeat this over and over again. So we're going to process all the courses with no incoming edges and delete those nodes outgoing edges. And then we'll repeat it, repeat it, repeat it, repeat it. And eventually, once we've gone, if we're able to get through all the courses doing this, we're good. We'll return the result. But if there's ever a point where we still have nodes that we have to process, but all of them have at least one incoming edge, so they essentially none of them have an in degree of 0, then that means we have a cycle, and that means that it's impossible to return a valid topological sort, which means that that two classes are a prerequisite of each other, which means it's not possible to take all the courses. Okay, so let's continue. So we created our adjacency list. We need to keep track of our incoming edges. So I'm just going to call this in degree. So in degree is just the number of incoming edges equals new int. It's going to be set to the length of num courses. And now we need to populate our adjacency list. So let's loop through all of our prereqs. Let's go with edge into prerequisites. Yeah, I was debating what I should call the variable name. So for every edge in our prereqs, then we can add that to our adjacency list. So I'm gonna use it. I'll explain what this method is if you don't recognize it. Compute if absent. So we're mapping the prereq. So this is the prereq to its list of courses that it's a prereq for, and then we're gonna add the course that it's a prerequisite for. So we have to take this course in order to take this course. And what I'm doing here is compute if absent will create an array list if this key does not exist. If the key does exist, then it's going to return the previous array list that we created, and we'll just use our existing array list and add in that course. Okay, so and now we have to increment the number of incoming edges for this guy because, let me just copy, yeah. So okay, so this is the prereq. Because this is the prereq, that means that it has an outgoing edge into this class. So this class or course, whatever, has an incoming edge. So we need to increment the number of incoming edges to this course. Okay. So now we can start coding out our BFS, our breadth first search. So create a queue of integers. This is just the courses. Q equals new array dq. And we want to loop through all of our courses that have 0 incoming edges. So we want to go through, just say int I equals 0, I is less than in degree, dot length plus I. Okay, and if in degree at I, if it equals 0, so that means it has no incoming edges, and this is essentially the course, right? I is the course, then we can add it to our queue. Okay, and now we can do our breadth first search. So while the queue isn't empty, we want to take this node out of our queue. So, or we want to take this course out of our queue. So this would be, we'll just call it course equals queue.pull. And okay, so we need a result, right? To return, we need to return some sort of we need to create an array to return the topological sort of our courses. So let's create a result equals new int. So just be num courses. And we're going to store this course in our result. So, and oh, we need a index. So I'm just going to call this order. And this is just going to, this order is going to be the index into this result. Let's just go with int I. Int I works just fine. So we'll just say int I equals 0, and this is the index into this result. So the result at I, so the result at 0 equals the course, the first one that we take out. Okay. And now we need to loop through all the neighbors of this course and delete those outgoing edges, or simulate deleting those outgoing edges. So if adjacency list contains this course, then loop through the neighboring courses. So adjacency list get course. So we're looking through all the neighboring courses here, and we want to so we need to subtract. So we're simulating deleting the edge, right? So we need to subtract the neighboring edge, and if it hits 0, then we want to add it to our queue. So offer the neighbor. Okay. So yeah, we loop through all the neighbors, all the neighboring courses, deleting the edge, and if it hits 0, then we put that class or neighbor into our queue. All right. Now, I think, is that it? I think we're done. Now we just return our result. And okay, but before, there's one last thing we have to do, and it's very simple. So if this I does not equal the number of courses, that means that we weren't able to process all the courses in our breadth first search, because that means that at some of the nodes didn't hit 0 for the in degree. And if not all the nodes are able to hit 0, that means that we have a cycle. So because essentially, if we should have been able to remove all the edges incrementally, but if we weren't able to, then it's because at least two nodes had at least two nodes were prerequisites for each other. So because if you have a cycle, then it's just as impossible. So anyway, so if I is equal to num courses, oh, we didn't increment I here, so we got to post increment here. So yeah, my bad. So hopefully you're still following along, but like we need to store the course at this index, and then we increment the index for the next course, right? And then eventually I should equal the number of courses, and we go ahead and return the result. Otherwise, if I never equals number of courses because we weren't able to add all the courses to our result, then that means we had a cycle, so we're just going to return an empty array. Let's run it and submit it. Cool, and it works. So yeah, that's how you do this problem with using Kahn's algorithm. You just process the courses with no incoming classes or edges, and then delete those outgoing edges, which we did here. And then if it ever hits 0, then you add those courses to our queue, and then we're good. Or if we're able to add all the courses, then we have a valid topological sorting. So time complexity, this just ends up being OV plus E because of our breadth first search here. And the time complexity is going to be OV plus E as well because of our adjacency lists. All right, so that takes care of this problem. If you like the video, you can give it a thumbs up and you can subscribe if you want. Cool, bye.